iteratively partition feature space. And no attempt is made at doing this optimally. So this is done greedily. And secondly, one estimates the class or the posterior probability for a class in each partition. And ideally, I would have liked to now copy the same data set I had on the blackboard before. So we had the one. So we have here a 2D feature space. It's much easier for me to use here numerical features as opposed to, all right, good. And now what the method does is it iteratively splits these samples. And now there are different ways of splitting. The predominant way traditionally in this line of work would be to split using only one axis at a time. Yeah, so we can ask ourselves, how good is each conceivable split? Yeah, so this split doesn't do anything. This split here, not so bad, because I now get one partition, which is only the circle class, and another partition, which is mixed. This one is even better. Yeah, I get 3 circles. Here, it starts to get worse because I now get a mixture of circles and crosses. That one maybe is not so bad because here I have only crosses beneath and only circles above. Okay, so we can evaluate the merit of each of these splits. And I get a merit score. So let's say if I put here the desirability of splitting, you know, it's, I would say, pretty good at the beginning because I create a pure partition and then it sort of drops and then it comes up again. All right. Now let's do the same thing for the other axis. And here, you know, I've not written anything. This would be something like desirability of splitting, yeah? No matter how precisely we define it. We can now try this. Okay, that's good. I create one pure partition. That's even better. You know, 4 crosses on one side. Okay, it gets a bit worse. This one is actually great. Huh? I have almost pure split on the right, pretty pure split on the left. So if I make a similar, you know, score here of desirability, it's pretty good throughout. And here, it's pretty good throughout. And now in absolute terms, you know, which one would we prefer? Would we prefer to make this split, which separated 3 samples from the rest? Or would I prefer that split, which is almost perfect, you know, almost perfectly separates my training data? I think we would prefer that split. Yeah? So this could be our first partitioning of feature space. And now we continue separately on each side. Yeah? So on this side, I can again ask, how is each of these splits? How is each of those splits? And then I decide maybe to take that one here. Here on that side, it becomes more tricky, actually. You know, it will take quite a few splits to separate out these circles. Or I do early stopping and say, I stop here, and these are the partitions. And I simply decide on this, in this partition, I'm going to predict the plus class or the cross class in this one also. And in this partition, I'm going to predict the circle class. And if I now ask for the decision boundary, well, here I predict the same class, so there's no decision boundary. So my decision boundary would look something like this. Yeah, this would be the decision boundary. Okay. So much, so good for the principle. And now we can discuss lots of details. Yeah? We can discuss, what exactly, what did I plot here? And there's also the fair question of, should I really use axis orthogonal splits or not? I think no. Okay, but let's look at some of these choices. So what one typically uses is some kind of uncertainty measure. And I can look now for each partition, what is the fraction of points from one class. So let's say I put here fraction of samples. Let's pretend that we work only with 2 classes from class 1. So if I'm here, I have a pure partition. There are only class 1 examples there. Here I have a pure partition. There are only samples from the other class. And in between, well, things are more mixed. And now we can have different, so we want something that is larger in between and that is 0 here. And now there are different choices what we could do. There is, for example, I could do this, or I could do that. That's a parabola. Or I could have something which is infinite slope here at the origin and infinite slope here. And all of these have been proposed, and all of these are important examples. Yeah, so this here would be the entropy. So if I'm calling this here P, then this would be minus PLN P. This one is the Gini index. The Gini index, you might have read this in newspapers. This is measured to, it measures inequality. Yeah, so it was proposed by some fascist, but it's still used nowadays to look at, for example, the inequality of the distribution of incomes across a society. Or the third one is also called misclassification error. So the third one says, okay, I'm predicting the more likely class, and what's the fraction of errors that I'm making. Yes, so for example, on the right-hand side here, I'm always going to predict class 1, and here my prediction has an accuracy of 100%. Here, if I predict class 1 here, but really it's half-half, my accuracy is 50%, and so between them I interpolate linearly as I move my threshold. And then we need a recipe to decide which split do we want to use, because these extreme splits, like let's say this one here, it creates a nice pure partition on the one side, but it only pleases a single sample. So we somehow need to take into account how many samples are there at all, or how much progress are we going to make in classifying our training data set. And this is measured by an uncertainty reduction. And now, this does not follow from, first principles of statistics. It's just a suggestion, and a suggestion which happens to work well. uncertainty reduction by introducing a new split. And if I'm calling these uncertainty measures here H, I'm using H because the entropy would be H, then we can look at what's the age of our current classification. And here, why is it called decision tree? Because this iterative partitioning that corresponds to a tree. Yeah, so we start at the root node, and then the first split we made, we asked, is x1 larger than a certain value? And if no, I get this partition and I already end, I predict the class plus. If, on the other hand, my observation, so here I'm asking, is x1 greater than some threshold? I'm calling this first parameter here theta1. If no, I go left. If right, I'm on this side here. Then I here have another split. So I have another node which now asks a question about x2. It asks, is feature x2 larger or not than some threshold theta2 question mark. This is also a node in my tree. And then again, there is a no answer in which I will predict the class plus. And there is a yes answer in which I will predict the class circle. Okay, this is why this is called a tree, and this would be a node in the tree. And this is what I mean if I now say we're looking at the uncertainty at some node minus, and now we look at how many samples are sent to the left or to the right side of that node. Yeah, so L is number of samples going down the left branch. And accordingly, we have R for number of samples going down the right branch. And then for a node, this would be called the left child, and this would be called the right child. Okay, and so now what we consider is the impurity of the current node. We consider the impurity of the resulting left or right child, depending on what question we ask. And we also take into account actually how many samples go down this left or this right path. And this we can either do until we get pure nodes. So we can either do this until pure partitions result, or we can do it until maybe some maximum depth of the tree, for example, is reached, or until some minimal number of training samples resides in a particular node. Yeah, we can say if there are only 5, if I have a data set of 1,000,000 points, and if there are only 10 points left in a partition, I'm not going to split that any further. Yeah, and you can invent many other criteria here. And these are called early stopping criteria. All right, and if we do it until we get pure partitions, we're going to get perfect fit on our training data. So in this particular case here, but of course, we are normally not going to do perfectly on our test data as well. So what we have is quite a bit of overfitting if we use just a single tree and if we train it until purity. And these early stopping criteria here, they are meant to reduce overfitting. Now, an alternative to using a single tree is to use a whole ensemble of trees, which I'm running out of time to talk to you about. So I'm coming to a premature summary. There's so much more to say about decision trees. This is a mini summary. It is extremely fast. It is fast to train because we make these decisions greedily. It is also fast at test time because the depth of a tree is normally only logarithmic in the number of training samples. So it's fast at train and test time. It ingests features on either the nominal or the ordinal scale, on either the nominal scale or the interval scale. It has other interesting properties. For example, if we use, for this particular choice of split functions, when we say we split only along one axis, we can use any monotonous transformation of our axis. Like, I could take the log of this axis or the square root, or I could take the square of it. This will not at all change the resulting structure of the tree. And this can be an advantage if we don't know how we should transform our data. Because the other methods that we've discussed, quadratic discriminant analysis and so on, if I use more general monotonous transformations, that would result in different decision boundaries. So these splits along single axes, which are also called monothetic splits, these are immune to monotonous transformations of the coordinate axes. And then we have many more degrees of freedom in this class of methods. So we can have other choices that are possible, for example, for the splits, because they need not be axis orthogonal. Yeah, we could also have oblique splits. Yeah, we could iteratively partition our training data like so. So we can generate pretty complex decision boundaries with fairly small trees. The decision boundary here maybe could look like so. And then this one here is superfluous, I'm sorry. And they can also be aggregated in ensembles. And these ensembles, they help combat overfitting, and they give us new degrees of freedom in the design of the method. They allow us, they give us new means of estimating the relevance or the importance of certain coordinate axes. So actually, there are very many good things to say about this class of methods. There are many more good things to say, but time is short. And we have so much more ground to cover in this lecture, so I'm leaving it here. And I'm looking forward to seeing you again next week.